Hi, I'm Stefan Mabry, and I'm here with Pierce Novak. Today we'll be looking at vision transformers and detention mechanisms and explore how they're used in the featured surgical analysis paper. At a high level, computer vision enables machines to analyze medical images and video with the precision of expert clinicians. That capability is driving advances in surgery, diagnosis, and patient monitoring. First, in surgical or robotic surgery, AI assists in planning, risk assessment, and real-time guidance. It also is being used for augmented reality overlays during operations and for monitoring patients after surgery. Second, in diagnostic imaging and analysis, computer vision supports radiology, pathology, and dermatology by detecting subtle patterns that can be hard to spot. This includes early cancer detection, fracture identification, things like hairline fractures that are really difficult to see in an image, and also automated triage of medical images to reduce the delays in getting the results, as well as lightening physician workload. Finally, in patient monitoring and workflow optimization, vision systems track movement and recovery progress in real time. They also streamline hospital operations with automated charting, surgical video review, and anomaly detection, improving both safety and efficiency. The system, called SACE, or the Surgical AI System, it's a very elegant name, or very creative name. It was developed by Kivesa and colleagues. It unifies three things that were usually handled separately. The first is recognizing surgical subphases, which are the different parts of a case in the OR, then classifying gestures that clinicians make during the surgical encounter, and assessing surgical skill. One of the most important findings is that the model worked across settings. So it wasn't just tied to one hospital or one group of physicians. It's generalized to new hospitals or different physicians and other surgical procedures even, which is a pretty astounding thing because the data from these different hospitals or different types of procedures are different. And so to be able to compare them across and get the same kinds of results is pretty phenomenal. And that's actually critical for the adoption in the real world. And then finally, the authors, they placed a big emphasis on the explainability and the outcomes. So using attention maps, they could show which frames of the model were used to make the predictions. And early evidence suggests that the skill assessments in the model that were generated were linked to actual patient outcomes, which means that this is a clinically relevant study. The explainability portion of it is really interesting to me because it's a difficult area to solve today, to understand why a model is saying what it says, and they did a really elegant explainability mechanism using attention. So the paper used several AI methods. It talked about a vision transformer, which is what we'll dive into, that extracts spatial features from surgical frames. And then it had a supervised contrastive learning, which separates different surgical actions. It used dual input streams combining RGB frames and optical flow. And it had an ensemble interface it stabilized the predictions across multiple models. And then it used an attention mechanism to highlight critical frames and improve interpretability. So we selected two methods to dive deeper into and explain for this project. So the first is visual transformers, and then the second is attention mechanisms. So starting with the vision transformer, it's the backbone of this SACE system. The model takes the surgical video frames and breaks them into small image patches, and then uses self-attention to capture relationships between surgical tools, tissue edges, and anatomical structures. So in this paper, the VIT, or vision transformer, it was pre-trained on a very large data set and then frozen at that point. So it gives it a robust spatial features to work with. And then the transformer can handle long and variable video sequences, which is not something that like convolutional models can support easily today. They break down at the longer video lengths where the transformer can handle longer segments of video. And these encounters can be hours long. So this means that the visual transformer it's a great AI model to apply to clinical videos. So then now for the attention mechanism. So that's what allows the system to focus on like the most relevant frames within the surgical videos, rather than treating every frame equally. Self-attention models, both the short-term actions like a quick needle adjustment, or the long-term patterns within the video, like studying the entire suturing sequences, which is like the part where you're using the needle and thread to close the wounds or the incisions. So on top of that, the attention weights can be then visualized so that surgeons can see like exactly which frames influence the model's decision, and that makes the outputs explainable and clinically interpretable, which is the key to that real world adoption we talked about. So how does it work? So I'll have 2 slides on vision transformers. I'm going to give you a high level, and then we'll go in a little bit deeper. So the simple breakdown is, step 1 is the input of the image. So the image is divided into fixed sized patches. So you cut it into like little tiles essentially. So each image in a frame, and then each frame in the video. So then each patch is flattened into a vector, and then we add both the positional embedding, so like where is it in the model, and where is the slice or the patch within the frame. And then so that way the model knows where the patch came from, and then a special class token will then later be attached that will represent the overall image. And then the second step is the transformer and encoding. So the sequence of patches are fed into the transformer, and so that's where the multi-head self-attention comes in. So it allows the model to like learn the relationships between the different patches. And the transformer layers also include feed-forward networks and normalization to refine the features themselves. And then the third step is this classification phase. So after the encoding, the class token is then pulled out and passed into a classifier head, and then that token now carries the information that's needed to produce the final prediction. And so they're really thinking about like which gesture is being performed and how skilled the action was that that was being made. So like there's needle driving, for example, and so the idea is this is a needle driving action, and it was done at a high degree of skill or a low degree of skill. This is a picture that we took from the paper that we're talking about, which is that image is worth 16 by 16 words. It's actually a really delightful name because they're cutting their images into 16 by 16 pixel squares. So this diagram shows the vision transformer workflow in a more visual way. So starting at the bottom, over in the bottom left here, the image is divided into patches. Those are the 60 by 16 frames. Each patch is then flattened into that vector. That's done here. So it's a linear projection into flattened patches, and then you combine it with that positional embedding. So you have a patch and positional embedding tacked together, and that way the model then knows what this thing is, or like this is the patch, and this is where it came from. And then they're going to add a special class token, which will eventually carry the overall representation of that image. And then those patch embeddings are then passed into this transformer encoder. And so inside the encoder, the multi-head self-attention will learn the relationships between the patches, and then there'll be the normalization and the feed-forward layers So in this case, this is the encoder itself on the far right side. So you'll take the embedded patches, they'll be passed in, they'll be normalized, then you get the multi-head attention, and we'll cover the attention in a second. That's critical to this paper. Then we'll normalize it again, and then that multi-layer perceptron, and then it'll come out. And each step is passing forward, passing forward the information from the previous phase, so that it's stacking the predictions. So finally, then the class token's pulled out up here, top left. This is the MLP head here and here. So they pull out the class token and then feed it into this classifier. In this case, it was a feed forward network. And then, oh, sorry, it was an MLP. So it was a multi-layer perceptron. That's the classifier in this case. But you can use any classification model you want in this place. This is the one that they selected. And then that'll detect then what the action is, what the gesture is that's being done, as well as the quality. So that's what they're classifying. So this visual, ties everything together. The patches go in, the relationships are learned, a single class token comes out, it carries through the information from step to step to step, up the chain, and then it's passed into the classifier, which then makes that final decision. One thing I find really cool about this, transformer models in general, is that it's not just one AI that's working. It's like a pipeline of AIs that are working together to achieve this one goal of classification, and so I find that pretty awesome. I'm going to hand it over now to Pierce to go through attention and then close us out.
Now we're going to be talking about attention, specifically scaled dot product attention and multi-head attention. For scaled dot product attention, imagine you're trying to figure out which parts of a sentence are most important when translating it into another language, say English to German. This diagram shows how a computer model does that using something called attention. For the starting point, you have three things: queries, represented by Q, keys, represented by K, and values, represented by V. Think of Q as a question that asks, what's important here? K are labels that help match the question, and V as the actual information we care about. Step 1 is matrix multiplication. The computer first compares the queries with the keys by multiplying them together. This is like checking how well each label, K, answers the question, Q. Step 2 is scale. The result can get really big, so the computer divides it by a number to keep things manageable. This is like turning down the volume so it's not too loud. Step 3, mask. Sometimes the computer ignores certain parts, like future words in a sentence, by adding a mask. This step isn't always used, but it helps focus on the right stuff. Step 4, softmax. The computer turns the scaled numbers into scores that add up to 1. Like giving a percentage of importance to each part, this is the attention part, deciding what to focus on. Step 5, matrix multiplication again. These attention scores are then used to pick and combine the values, giving more weight to the important parts. This creates the final output. So this process helps the model figure out which words or pieces of data to pay attention to, making the translation from English to German or prediction better. Multi-head attention. Now imagine you want to look at a sentence in different ways at the same time, like checking the meaning, the grammar, and all the context all together all at once. Multi-head attention does that by using multiple heads to look at the data. The starting point is, again, you have queries represented by Q, keys, which are K, and values V from the input data. Step 1 is linear transformations. The computer splits the work into several heads, let's say 8 heads. Each head gets its own version of Q, K, and V by applying some math, the linear transformations, to look at different aspects. Step 2 is the scaled dot product attention for each head. Each head runs the scaled dot product attention process we just talked about. So every head figures out what's important in its own way, using its own Q, K, and V. Step 3 is concat. After the heads finish, the computer puts the results together side by side, like stacking different perspectives into one big picture. Step 4 is linear. Finally, the computer adjusts this combined result with more math to make it the right size and format for the next part of the model. This multi-head approach is like having several helpers looking at the same sentence from multiple different angles, which helps the model understand things better and faster, especially for complex tasks like translating long sentences. In conclusion, scale-product attention is like focusing on one way to understand importance in the data. Multi-head attention is like using multiple ways at once to get a fuller picture, making the model smarter and more flexible. Both help the computer decide what to focus on, but multi-head does it with more teamwork. Now we turn our attention to vision transformer and attention in the paper. This slide covers how visual transformers and attention were used in our selected paper. On the vision transformer side, the model was applied directly to surgical video frames by splitting them into patches. It learned to distinguish skill levels in tasks like needle handling and driving, and it consistently classified gestures in ways that matched or even outperformed human evaluators. On the attention mechanism side, the model could highlight the most relevant regions of the image during a surgical action. That made the decisions interoperable, as surgeons could actually see where the model was focusing. Even those attention maps provided actionable feedback, linking model outputs directly to surgical technique. Note, this is rare in AIs today, so it's really cool to see a paper do explainability well with the tools we have today. The paper that we chose for this presentation was a vision transformer for decoding surgical activity from surgical videos from the Nature Biomedical Engineering. The two reference papers we used were An Image is Worth 16 by 16 Words, Transformers for Image Recognition at Scale, and the foundational Attention is All You Need paper. Any questions? We look forward to answering your questions online in the Q&A section. Feel free to post any questions and we will answer as we are able. Thank you for your time today, and feel free to get in touch. You can find us both on LinkedIn, Stefan in Madison, Wisconsin, myself in Fargo. Otherwise, send us an email. Connect with us on LinkedIn, and we look forward to working with you in the future. Thank you. Have a great day.